Before you picture wires strapped to someone's arm and a needle jumping every time they stretch the truth, let's clear something up immediately, because the phrase quantum lie detector genuinely does sound like it belongs in a spy movie rather than a physics journal. This has nothing to do with catching a human being in a lie. What an international team of physicists actually built and successfully tested is something considerably stranger and, in its own way, considerably more important. A rigorous scientific method for catching quantum computers in a lie, specifically the lie of pretending to be quantum, when they are secretly just behaving like an ordinary, boring classical computer underneath all the marketing and impressive-sounding technical jargon. And the fact that scientists just proved this test actually works at a genuinely large scale might be one of the most quietly consequential physics results of the past year, one that goes straight to the heart of whether the entire quantum computing industry can actually trust its own multi-billion-dollar machines to be doing what everyone assumes they are doing, rather than simply taking impressive-sounding qubit counts and processing claims entirely at face value. To understand why anyone would need a lie detector for a computer in the first place, you need to understand a problem that has quietly haunted the quantum computing industry since its earliest days. Quantum computers are supposed to work by exploiting genuinely strange physical phenomena that have no equivalent in ordinary, everyday computing. Phenomena like superposition, where a quantum bit can effectively exist in multiple states simultaneously, and entanglement, where two particles become so deeply linked that measuring one instantly affects the other, no matter how far apart they are physically separated. These effects are what theoretically give quantum computers their extraordinary potential power. The ability to explore vast numbers of possible solutions simultaneously rather than checking them one at a time, the way a conventional computer, however fast or well-engineered, would ordinarily be forced to do. But here's the uncomfortable problem underneath all of that promise as quantum computers grow larger and more complex, packing in more and more qubits. It becomes genuinely difficult to verify with total certainty that a given machine is actually harnessing these strange quantum effects, rather than simply behaving in a way that looks impressively complicated on the surface, while secretly following the same fundamentally ordinary classical physics that governs your laptop or your phone. It helps to understand exactly why distinguishing genuine quantum behavior from a clever classical imitation is so much harder than it might initially sound. A sufficiently complex classical computer, given enough processing power and cleverly designed algorithms, can actually simulate many of the outward behaviors associated with quantum systems reasonably well, at least for smaller scale problems, producing outputs that look statistically similar to what a genuine quantum process might generate without actually harnessing any real quantum mechanical phenomena underneath the hood. This creates a genuinely tricky verification problem for physicists and engineers alike, since simply observing that a quantum computer produced an impressively complex or difficult to predict output does not, by itself, prove that output actually emerged from authentic quantum superposition and entanglement effects, rather than from an extremely sophisticated, but ultimately entirely classical, computational process running underneath a quantum-sounding label. The entire value proposition of quantum computing rests specifically on these systems, eventually outperforming classical computers by genuinely exploiting quantum mechanical phenomena that classical systems simply cannot replicate at scale, which means rigorously confirming that a given machine is actually doing this, rather than merely appearing to, represents an absolutely foundational scientific and engineering challenge for the entire field. This distinction matters enormously, and not just as some abstract philosophical curiosity confined to physics departments and academic journals nobody outside the field ever reads. Quantum computing companies routinely make bold public claims about qubit counts, processing power, and computational milestones achieved by their latest hardware, claims that investors, governments, and potential customers increasingly rely on when deciding where to direct billions of dollars in research funding and commercial investment. If a company's quantum processor is technically running calculations, but is not actually leveraging genuine quantum mechanical effects at the scale it claims to be, that distinction could mean the difference between a machine capable of eventually delivering on quantum computing's most transformative promised applications, and a much more mundane, considerably less powerful device dressed up in impressive-sounding quantum terminology. Verifying genuine quantumness, rather than simply trusting a company's own marketing claims or even its own internal engineering assessments, has become an increasingly urgent and pressing scientific and practical engineering challenge as the entire industry races toward larger and more complex machines. This is precisely where a physicist named John Bell enters the story, even though he died back in 1990, decades before anyone had built anything resembling a modern quantum computer. In 1964, Bell developed a mathematical framework now known as Bell's inequality, specifically designed to distinguish between two fundamentally different pictures of how the universe might actually work at its smallest scales. One picture, favored by Albert Einstein among others, imagined that particles carry hidden, predetermined properties even before anyone measures them, meaning the apparent randomness and strange correlations physicists observed in quantum experiments might simply reflect our own incomplete knowledge of some deeper, more conventional underlying reality that a future, more complete theory would eventually reveal in full detail. The other picture, the genuinely strange one that mainstream quantum mechanics actually describes, suggests that particles do not have definite properties until the moment they are measured, and that measuring one particle in an entangled pair can instantaneously influence the measurement outcome of its distant partner, a phenomenon Einstein famously and dismissively called spooky action at a distance, because it seemed to directly violate his own deeply held intuitions about how the physical universe ought to reasonably behave. This particular disagreement between Einstein and the emerging field of quantum mechanics has a genuinely fascinating history worth briefly understanding, because it illustrates just how deeply strange and counterintuitive these ideas remained even to some of the greatest physicists of the 20th century. Back in 1935, Einstein, working alongside physicists Boris Podolsky and Nathan Rosen, published what became known as the EPR paradox, a thought experiment specifically, designed to argue that quantum mechanics, as it was then understood, must be an incomplete description of physical reality. Their argument centered on exactly the kind of entangled particle pairs discussed earlier. Einstein and his colleagues reasoned that if measuring one particle could instantaneously determine the properties of its distant entangled partner, then either information was somehow traveling faster than the speed of light, something Einstein's own theory of relativity specifically forbade, or those particles must have possessed definite predetermined properties all along, hidden variables that quantum mechanics simply had not yet identified or counted for in its own mathematical framework. For nearly 3 decades following this famous paper, this remained largely a philosophical debate rather than something physicists could actually test experimentally, since nobody had yet devised a way to definitively distinguish between these two competing explanations using real physical measurements rather than pure theoretical argument. Bell's 1964 breakthrough was precisely that missing piece, transforming what had been an abstract philosophical disagreement into a concrete, testable scientific question with a definitive, experimentally verifiable answer. This transformation from philosophical speculation into rigorous experimental science represents one of the great triumphs of 20th century physics. And it is precisely this same underlying experimental tradition, dating back more than 60 years to Bell's original theoretical insight, that the Leiden, Beijing, and Hangzhou research team drew upon and dramatically extended when they successfully scaled this exact verification approach up to 73 qubits within a modern quantum computing processor. Bell's genuinely brilliant insight was realizing that these two competing pictures of reality actually make different, testable, mathematical predictions about the statistical correlations you should observe when running specific kinds of experiments on entangled particles, predictions precise enough that a sufficiently careful laboratory experiment could actually distinguish between them rather than leaving the question permanently confined to philosophical debate. If you run enough of these experiments and the resulting correlations exceed a certain mathematical threshold, defined precisely by Bell's own inequality, that specific result becomes essentially impossible to explain using any theory built on Einstein's hidden, predetermined properties picture of reality. Decades of increasingly sophisticated laboratory experiments, eventually recognized with the 2022 Nobel Prize in Physics, awarded specifically for this body of work, have consistently confirmed that nature really does violate Bell's inequality, meaning genuine quantum weirdness, not some more comfortable conventional hidden explanation, actually governs how our universe fundamentally works at the smallest scales. A conclusion that took the scientific community the better part of a century to fully and rigorously establish. If you are finding this breakdown genuinely fascinating so far, take a second to like and subscribe, because this channel covers exactly this kind of deep physics story, the ones that sound abstract at first but end up having genuinely enormous practical consequences for the technology reshaping our world. For decades, Bell's test worked beautifully on small systems involving just a handful of particles, a small number of photons or trapped atoms carefully prepared and measured inside a laboratory. The genuinely difficult challenge physicists have wrestled with more recently involves scaling this exact same verification approach up to the much larger, far more complex quantum systems found inside modern quantum computers, machines containing dozens or even hundreds of interacting qubits simultaneously. Directly measuring the full SET of Bell correlations across a system that large becomes computationally and experimentally overwhelming, using traditional methods, since the number of individual measurements required to properly characterize all the possible correlations. between many interacting particles grows explosively as you add more qubits to the system, quickly outpacing what any realistic laboratory setup could actually accomplish within a reasonable amount of time. To put this scaling challenge in more concrete terms, imagine trying to verify that every single pair of people at an enormous stadium concert is secretly coordinating their movements through some kind of instantaneous, unexplainable connection, rather than each person simply making their own independent choices about when to clap or cheer. With just two people, checking for this kind of coordinated behavior is straightforward. You simply watch them both and compare their timing directly. But as the crowd grows into the thousands, the sheer number of possible pairs you would need to check individually explodes combinatorially, quickly becoming a physically impossible task to complete through direct, brute force observation alone, even if you had unlimited time and attention to devote to the task. Quantum physicists faced almost exactly the same mathematical explosion when trying to directly measure Bell correlations across many interacting qubits simultaneously, since the combinations required to fully characterize all the possible correlations between many. Entangled particles grows so explosively that direct measurement becomes utterly impractical. Well before you reach anything close to the 73-qubit scale the Leiden, Beijing, and Hangzhou team ultimately managed to successfully test, the variational quantum circuit approach the research team specifically developed represents a genuinely elegant mathematical workaround to this combinatorial explosion problem. Rather than attempting to directly catalog and measure every single possible correlation across their entire 73-qubit system, an approach that would have required an utterly impractical number of individual measurements, the team instead designed a clever indirect strategy built around a specific mathematical quantity, the total energy of a carefully constructed quantum state, that quantum devices can already measure relatively efficiently using existing experimental techniques. By mathematically proving that achieving a sufficiently low energy level in this specific, carefully engineered quantum state would be fundamentally impossible under any classical non-quantum explanation of the underlying physics, the researchers effectively transformed an experimentally impractical direct measurement problem into a considerably more tractable indirect one, allowing them to draw airtight conclusions about genuine quantum non-locality without ever needing to perform the kind of exhaustive, combinatorially exploding direct measurement process that would have made the specific experiment essentially impossible to actually carry out in any real laboratory setting. This is exactly the challenge an international team of researchers from Leiden University in the Netherlands, Tsinghua University in Beijing, and Zhejiang University in Hangzhou set out to solve in their published results, which first appeared in the scientific literature in the latter half of 2025 before continuing to generate significant follow-up discussion and related research throughout 2026, represent a genuinely clever engineering solution to this specific scaling problem. Rather than attempting to directly measure the full, overwhelming complexity of Bell correlations across their entire quantum system all at once, the research team, including theoretical physicists Jordi Tura, Patrick Emons, and PhD candidate Mingyao Hu from Leiden, working alongside experimental physicists, including Chao Song from Zhejiang University, developed what they called a variational quantum circuit approach, specifically designed to probe these correlations far more efficiently than earlier, more brute force methods had allowed. The key insight behind their approach involved reframing the entire verification challenge around a task quantum devices already handle relatively well, minimizing energy. Rather than trying to directly measure every possible Bell correlation across their quantum system, the researchers instead prepared a carefully designed quantum state and specifically looked for energy levels significantly lower than what any classical non-quantum explanation could possibly account for, essentially using energy minimization as an indirect but mathematically rigorous proxy for detecting genuine quantum non-locality. The deep, spooky correlation effect Bell's original test was specifically designed to reveal. Using this clever technique on a superconducting quantum processor, the team successfully demonstrated genuine multipartite Bell correlations involving up to 73 F particles earlier Bell test experiments had traditionally involved, and by a considerable margin, the largest system in which this kind of test had ever been successfully and rigorously demonstrated. The statistical strength of this particular result deserves special attention because it speaks directly to just how confident physicists can genuinely be in these findings. According to Jordi Tura, one of the paper's co-authors, the difference between what the researchers actually observed and what any classical non-quantum explanation could plausibly produce measured a staggering 48 standard deviations, making it, in his own words, almost impossible that the result was simply due to random chance, To put that number in perspective, for anyone unfamiliar with statistical significance in physics research, most groundbreaking discoveries across physics, including the famous 2012 announcement confirming the existence of the Higgs boson, are considered definitively confirmed once they reach a threshold of roughly 5 standard deviations of statistical confidence. A result reaching 48 standard deviations represents a level of statistical certainty so overwhelming that it leaves essentially no realistic room for doubt about whether the observed quantum correlations were genuinely real, rather than some kind of statistical fluke or measurement artifact. It is worth dwelling on the statistical comparison a bit further, because it helps convey just how extraordinarily confident physicists can genuinely be in this particular result compared to many other scientific claims people encounter in ordinary life. A 5 standard deviation result, the standard threshold physicists typically require before declaring a new discovery definitively confirmed, corresponds to roughly a 1 in 3.5 million chance that the observed result occurred purely by random statistical accident, rather than reflecting a genuine underlying physical effect. Scaling up to 48 standard deviations pushes that probability of random chance down to a number so astronomically small that it becomes genuinely difficult to express in any intuitively meaningful way, vastly smaller than the odds of winning even the most improbable lottery jackpot multiple times in direct succession. This level of statistical rigor reflects physics as a discipline operating at its most careful and exacting, deliberately setting an extraordinarily high bar for declaring any result definitively true, precisely because claims this consequential, ones that could reshape how the entire scientific and investment community evaluates quantum computing hardware going forward, genuinely deserve this kind of exceptionally rigorous statistical scrutiny before anyone accepts them as settled, established fact. This experiment's specific scale also deserves comparison against the broader historical arc of Bell test experiments dating back to the earliest laboratory attempts in the 1970s and 1980s. Early pioneering experiments, including landmark work conducted by physicist Alain Aspect in the early 1980s, which later contributed to his own share of the 2022 Nobel Prize in Physics, typically involve just pairs of individual photons, a scale that, while scientifically groundbreaking and historically important at the time, was almost unimaginably far removed from the 73-qubit. Many particle systems successfully verified through this newer research. Over the following decades, physicists gradually scaled these experiments up incrementally, closing various theoretical loopholes that skeptics had identified as potential alternative explanations for the observed correlations, and gradually extending Bell test verification to progressively larger and more complex systems as experimental techniques and theoretical understanding both continued to mature. The jump from small handfuls of individual particles to a genuinely large scale 73-qubit quantum processor represents not an incremental refinement of this decades-long experimental tradition, but rather a genuinely dramatic leap forward, one specifically enabled by the clever variational quantum circuit technique the Leiden, Beijing, and Hangzhou research team developed to sidestep the otherwise prohibitive combinatorial measurement challenge that had long constrained how large these kinds of rigorous verification experiments could realistically become. What makes this particular achievement genuinely significant, beyond simply representing an impressive standalone physics demonstration, is what it reveals about the trajectory of quantum computing hardware more broadly. As Chaosong and his co-authors specifically emphasized in describing their own results, this experiment did not simply confirm that quantum computers are continuing to grow larger in terms of raw qubit count. It specifically confirmed that these increasingly large machines are becoming more authentically, verifiably quantum in nature as they scale up, rather than merely becoming more complicated in ways that might not actually reflect genuine underlying quantum mechanical behavior. This distinction matters enormously for an industry that has occasionally faced legitimate skepticism from outside physicists, specifically questioning whether certain widely publicized quantum computing milestones and claimed quantum advantage demonstrations genuinely reflected authentic quantum mechanical processing, or whether some of those claims might have been achievable, at least in principle, through sufficiently clever classical computing techniques that simply had not yet been fully explored or optimized by skeptical outside researchers. This verification challenge connects to a broader, ongoing pattern of scientific scrutiny that has periodically challenged specific quantum computing claims over the past several years. Various announcements of so-called quantum supremacy or quantum advantage, meaning demonstrations where a quantum computer supposedly solved a specific problem faster than any classical computer realistically could, have occasionally faced pointed challenges from independent research teams who later developed improved classical algorithms capable of closing much of the originally claimed performance gap, suggesting the original quantum advantage claims may have been somewhat overstated or based on insufficiently optimized classical comparison benchmarks. This particular dynamic played out publicly on more than one occasion throughout the broader history of quantum computing's development, and it is genuinely instructive to understand exactly how these disputes have typically unfolded. When Google first announced achieving quantum supremacy back in 2019, claiming its quantum processor had completed a specific calculation in minutes that would supposedly take the world's most powerful classical supercomputers thousands of years to replicate, that announcement generated enormous excitement and extensive media coverage across the entire technology industry. Within a relatively short period afterward, however, researchers at IBM published their own competing analysis, arguing that a sufficiently optimized classical supercomputer could actually complete the exact same calculation in a considerably shorter time frame than Google's original claim suggested, dramatically narrowing the apparent performance gap between the quantum and classical approaches. Similar disputes have periodically resurfaced in the years since, with various companies announcing new quantum advantage milestones, only to face subsequent challenges from independent researchers who developed improved classical algorithms specifically designed to close the gap and call the original quantum claims into question. This recurring pattern of claim and counterclaim illustrates precisely why rigorous, mathematically airtight verification tools, like the newly demonstrated large-scale Bell test approach, carry such genuine scientific value for the broader quantum computing field. Rather than relying on an ongoing, potentially endless back and forth between quantum computing companies claiming victory and skeptical classical computing researchers subsequently attempting to match or exceed those results using improved conventional algorithms, a rigorous Bell test, specifically regardless of how cleverly optimized their underlying algorithms eventually become, a performance benchmark that sufficiently clever classical engineering might eventually catch up to or match through improved algorithmic techniques. A quantum system that genuinely violates Bell's inequality by 48 standard deviations has demonstrated something no classical computer, no matter how powerful or how cleverly programmed, could ever replicate even in principle, providing exactly the kind of definitive, permanently settled verification that ongoing quantum versus classical computational speed comparisons have historically struggled to provide with comparable certainty. Rigorous, mathematically airtight verification tools like this newly demonstrated large-scale Bell test approach offer the broader scientific community a genuinely independent, extremely difficult to fake method for confirming that a given quantum system really is exploiting authentic quantum mechanical effects, rather than relying entirely on a company's own internal claims or on performance comparisons against classical algorithms that outside skeptics might later determine were not actually optimized as thoroughly as they could have been. The practical real-world implications extend considerably further than simply providing bragging rights or reassurance for physicists working in academic research settings. As the research team themselves specifically noted, understanding and reliably harnessing genuine Bell correlations at this kind of meaningful scale could eventually contribute to more secure quantum communication systems, stronger forms of encryption built directly on these same underlying physical principles, and faster, more reliable quantum algorithms overall. Quantum key distribution, a method for securely sharing encryption keys that relies specifically on the same kind of genuine quantum non-locality. Bell's test is designed to verify, becomes considerably more trustworthy and verifiable as a security technology once researchers possess increasingly sophisticated, scalable tools for confirming that the underlying quantum hardware generating those security guarantees is actually behaving the way the underlying physics theoretically promises, rather than potentially harboring some subtle, undetected classical loophole that a sufficiently determined and sophisticated adversary might eventually learn to exploit. Quantum key distribution specifically deserves a bit more explanation here, since it represents perhaps the most immediately practical real-world application connected to this kind of large-scale Bell test verification. Unlike conventional encryption methods that rely on mathematical problems believed to be extremely difficult for computers to solve, quantum key distribution instead relies directly on the fundamental physical properties of entangled particles themselves, exploiting the fact that any attempt by an item disturbs the delicate quantum correlations involved in a way that immediately becomes detectable to the legitimate parties on either end of that communication. The security guarantee, however, only holds as strong as the underlying assumption that the quantum hardware generating and transmitting these entangled particles is actually behaving according to genuine quantum mechanical principles, rather than potentially harboring some subtle, undetected classical vulnerability that a sufficiently sophisticated, given quantum communication systems security claims genuinely hold up under the most demanding possible scrutiny, rather than resting on unverified assumptions about how the underlying hardware actually behaves at a deep, fundamental physical level. There is also a genuinely important trust and verification dimension to this story that extends well beyond quantum computing's own specific technical community, one relevant to anyone trying to make sense of The broader avalanche of quantum computing headlines and corporate announcements that have become increasingly common throughout 2025 and 2026. As governments, defense agencies, and private investors continue committing enormous sums of money toward quantum computing research and infrastructure, verification tools capable of independently confirming whether a given quantum system genuinely performs as advertised become an increasingly essential. Purely aspirational marketing claims across an industry that has, at various points over the past several years, developed something of a reputation for occasionally overselling incremental progress as more revolutionary and definitive than independent. Skeptical scrutiny later confirmed it actually was, a reputation that rigorous, independently verifiable tools like this one are specifically designed to help the field as a whole gradually overcome. It is worth being appropriately precise here about exactly what this specific breakthrough does and does not actually prove, since overstating its significance would ironically undermine the very rigor and scientific precision that makes this particular result so genuinely valuable in the first place. This experiment specifically confirmed that a 73-qubit superconducting quantum processor exhibited genuine, statistically overwhelming Bell correlations, providing extremely strong evidence that this particular machine was authentically leveraging real quantum mechanical effects at that specific scale, rather than secretly relying on some undetected classical workaround that a less rigorous testing method might have overlooked entirely. It does not automatically mean every quantum computer currently operating anywhere in the world has been definitively verified using this exact same rigorous standard, nor does it mean every previous claim of quantum advantage or debunked through this specific methodology, since each individual claim would still need to undergo its own separate, dedicated verification process before any such conclusion could be responsibly drawn. What it does represent is a genuinely important proof of concept, a demonstrated scalable technique that the broader scientific community can now potentially apply more widely across an expanding range of quantum computing hardware platforms as the underlying technology continues to mature and scale toward ever larger, more commercially significant systems. The broader significance of this achievement becomes clearer when you consider it alongside a parallel related demonstration that emerged from the University of Vienna just a few months later in the spring of 2026, in which researchers successfully placed a tiny, visible chunk of metal into a genuine quantum superposition, causing it to behave as though it existed in multiple physical locations simultaneously, another record-breaking demonstration specifically pushing the boundaries of how large and how physically substantial an object can be while still exhibiting unambiguous, experimentally verified quantum mechanical behavior. Taken together, these kinds of experiments, verifying genuine quantumness at increasingly large scales across different specific physical systems and different specific experimental approaches, represent a broader and genuinely exciting scientific trend. Physicists are not merely building larger and more powerful quantum machines. They are simultaneously developing increasingly sophisticated and rigorous tools for actually confirming those machines are doing exactly what the underlying quantum physics promises, rather than simply asking the rest of us to take that claim entirely on faith. At the University of Vienna, metal superposition experiment specifically deserves a slightly closer look, because the physical scale involved in that particular demonstration helps illustrate just how far experimental quantum physics has advanced in confirming genuinely strange quantum behavior across increasingly large, increasingly tangible physical systems. For most of quantum mechanics history, superposition and entanglement effects had only been convincingly demonstrated using genuinely microscopic particles, individual photons, electrons, or atoms, far too small for anyone to ever directly perceive with the naked eye. The Vienna team's achievement, successfully placing an actual visible chunk of metal, something you could theoretically hold between your fingers under ordinary circumstances, into a state of genuine quantum superposition, pushes the boundary of demonstrated quantum behavior into an entirely different, considerably more intuitively startling regime, one where the strange predictions of quantum mechanics start colliding directly with our own everyday, common-sense expectations about how solid, visible objects ought to behave in the physical world around us. Taken together with the 73-qubit Bell test result, these two experiments, emerging from entirely different research teams working on entirely different, specific physical systems, jointly illustrate a genuinely exciting broader moment in experimental physics, one where researchers are simultaneously pushing the boundaries of quantum mechanical demonstration along two distinct but complementary dimensions, scaling up the sheer number of interacting quantum particles involved in a single system on one hand, while scaling up the physical size and visibility of individual quantum objects on the other. Both directions of progress matter enormously for the long-term trajectory of quantum technology, since practical, commercially useful quantum computers will eventually need to reliably coordinate enormous numbers of interacting G-qubits simultaneously, while other emerging quantum sensing and quantum communication applications may eventually benefit from working with larger, more physically robust quantum systems than the extremely fragile microscopic particles. Quantum physicists have traditionally had to work with throughout most of the field's history. What makes this entire story worth understanding, beyond its genuine value as a fascinating piece of cutting-edge physics research in its own right, is the broader lesson it offers about scientific rigor and healthy skepticism in an era increasingly saturated with dramatic-sounding technology headlines and ambitious corporate claims. As quantum computing continues attracting enormous investment, intense media attention, and genuinely transformative promises about its eventual real-world applications, having mathematically rigorous, statistically overwhelming tools available for independently verifying those underlying claims matters considerably more than any single company's own internal marketing materials or self-reported technical benchmarks ever could on their own. Physicists did not simply build a clever party trick when they successfully scaled Bell's original 1964 test up to 73 qubits with 48 standard deviations of statistical confidence. They built a genuinely important piece of scientific infrastructure specifically designed to keep an entire rapidly growing, increasingly consequential technology industry honest about what its machines can actually do, verified not through trust or reputation, but through the same kind of rigorous, mathematically airtight physics that has reliably separated genuine scientific discovery from mere speculation for literal centuries. If this kind of deep dive into the physics, quietly underpinning and validating the biggest technology headlines of the moment, is exactly the kind of content you want to see more of on this channel, make sure you like and subscribe, because there is a great deal more of this story still waiting to unfold as quantum computing hardware continues scaling toward ever larger, more consequential systems in the years directly ahead, and as physicists keep developing ever more rigorous tools to make sure those systems are telling the truth about what they can actually do.